Hi, I'm Chamath Palihawadana. I'm here to present our work PhD, Mitigating Gradient Inversion Attacks in Federated Learning with Frequency Transformation. My co-authors are Nirmalie Wiratunga, Harsha Kalutarage, and Anjana Wijekoon. So we will be first doing a quick introduction into federated learning, attacks in federated learning, then the identified gaps, move on to threat models and the attack methods, then our proposed defense method, evaluation, and the summary. So what federated learning is a technique where users can train machine learning models in a decentralized manner without the need of sharing their data to a central server, also known as privacy preserved machine learning. So how federated learning works is there would be a server and a group of clients, and the server would have an initial global model which would be communicated to the clients. So this can be either for a group of selected clients or all the clients depending on their availability. So once the clients have the global model, they can train the model with their local data. So they can do an update step here. And then once the local update is ready, the clients can communicate the local model back to the server. And then the server would do a aggregation step with all the received models and create a new global model. And this process can be done in an iterative manner until there's a stable global model. If you move on to attacks in federated learning, there are two types of attacks. The first one is performance attacks. This is where the attacker would aim to attack the performance on the overall FL system. So this can be done by either poisoning the data or the model. The second type of attack is privacy attacks. This is very crucial for federated learning because federated learning is a privacy preserving technique and it's very crucial to be safe in terms of privacy. So there are two types of attacks here, gradient inversion and leakage attacks. So for our work, we have selected privacy attacks and the gradient inversion attacks to be specific, and then trying to do a method where we can mitigate this kind of attacks. So we have identified multiple gaps in this area. So first one is privacy attacks compromise the integrity of federated learning. So we have to make sure the privacy is preserved in our FL setting. Second, we have identified that the communication layer is the most riskiest and the largest threat surface in federated learning. Third, we have identified that gradient inversion attacks is a serious threat into FL. So the adversarial goal in these attacks would be reconstructing client's private data and its class label through the communicated gradients. So the attack would only have access to the gradients, not the data, and they would try to reconstruct the private information. So there are two types of attackers we have identified. First one is the server, which can be honest but a curious server. And third, we can have a man in the middle attack, snooping the packets from the data communication layer. So we have selected two attack methods to propose our defense mechanism. First one is deep leakage gradients, also known as DLG, and its improved version called improved deep leakage gradients. DLG is a well-known gradient inversion attack which uses a gradient matching technique. So the DLG process starts by generating dummy data and dummy gradients. Then by optimizing the dummy gradients to be close to the client gradients, the dummy data will be close to the real data. This is also shown in the diagram here. If you move on to our proposed defense method, we propose prune frequency-based gradient defense, PFGD. Here we perform two operations, frequency transformation and a pruning step. So the gradient inversion attacks are prevented by adding noise and the parameter reduction step by doing the pruning. If you look at the diagram below, after the local update, we would do a frequency transformation on the updated gradients and then a pruning, and then we would communicate it to the server. In order to add noise and parameter reduction, we use frequency transformation. The idea is to move away from the row space so that we can introduce sufficient amount of noise to mitigate gradient inversion attack while preserving the performance. Frequency transformation is commonly used in compression techniques and in image processing like JPEG. For our transformation function, we have used DCT, which is known as discrete cosine transformation, for its low computation cost and orthogonality. In the diagrams below, left shows the row space and right shows the frequency space. The advantage of this transformation is that frequency space coefficients are sorted by its significance, which allows us to efficiently prune. If you move on to the pruning function, the aim is to introduce sufficient noise again. So we could ignore all the least significant coefficients and we can make them basically zero and communicate to the server. This is our summarized algorithm, which we have the PFGD method and a method where an attacker can try to recreate by doing the inverse DCT as well. One of the key advantages of PFGD is its generalizability across other methods. So our method can be applied to existing federated learning techniques. And if you can see step 5 and 6, we would be adding a transformation function and then pruning function with alpha percentage, and then the server could have a inverse DCT function, which then used to aggregate the gradients. So by adding these 3 steps in a federated setting, we can basically use any other technique used in federated learning. Going on to our experiment, we have used MNIST dataset, 10 class handwritten digit recognition. We adapt the experimental settings from DLG and IDLG to make it comparable. We perform 100 attack iterations and on 1000 experiments which are randomly initialized. We have done these experiments in 2 variants. One is 1% pruning and 0.1% pruning. And for each experiment, we do a comparative study. So for that, we have 4 configurations. First one is the vanilla without any modifications. Then we have vanilla with pruning, which we just do the pruning on top of DLG and IDLG. And then we have applying DCT only, so that's the transformation step. Then our 4th configuration is DCT with pruning, so this is PFGD. And we have evaluated our method using mean squared error of the reconstruction. Before moving on to the experiment results, this slide shows the readability of images at different MSE thresholds. So as you can see, the first image is having very high MSE and it's completely unreadable, but if you can see when it gradually reduces across, we can start to see the image 9 appearing. So one of the important things we have observed is even at MSE threshold like 0.01, we can see the image as image digit 9. So this is a very risky situation in a federated learning setting where the client's privacies can be exposed like this. If we move on to results, our first results are on pruning 1%. So these graphs are at different MSE thresholds. So you can see MSE 1, 0.5 and keep on reducing. And we have 2 colors. So the blue color indicates DLG and the yellow color indicates IDLG method. And for each method we have 4 variants, configurations as discussed earlier. So what we have observed is when the MSE threshold is lowered, we can see that the IDLG and DLG pruned with frequency transformation, which is the last column in each of the graphs, has been reducing and it has basically become 0. And that means there are no images which have achieved that threshold 0.5, 0.1, 0.0, 0.5 and keep on going. So one of the riskiest things we have identified here is, as you can see, even at lower graphs, we can see vanilla method as leakages, and then it sort of gradually decreases, but it still has a high percentage of privacy exposure. Similarly, with pruning 0.1%, we can see very similar results, and when the MSE thresholds are gradually decreased, we can see our method has performed very well and defended attacks on gradient inversion. In summary, we presented our work on PFGD, and we have identified combination of DCT with pruning techniques have significantly enhanced the defense against gradient inversion attacks. And throughout the 1000 experiment runs, we did not observe any reconstructions when applying our method with an MSE below 0.9 for the 1% pruning method. So that's a very important results we have identified. And results highlight the resilience and efficacy of the proposed method. And we observed that the implementation of PFGD using frequency space has comparable performance, and PFGD can be easily applied to FL methods. Thank you for listening. Code and results are on GitHub, and you can visit us there. Thank you.
Yeah, my answer would be I don't know because we haven't tried with other data, just tried image data. But I agree with the point. Image data can actually easily reach the frequency domain compared to regular data. But maybe it was we, but it would be harm. I have one single data. So now current experiment is on MSTD. If we use more complicated, so here performance will be okay. Okay. Yeah, but my answer would be I don't know. Okay, but okay. Data, I can give you because with that is not performance, but you should try. Thanks.